So there was only one thing that didn't finish up with the rational functions last time. And this is basically the same sort of thing that we did with the polynomial functions, right? This business of getting sort of more precise graph of rational functions, of any rational function. And so this is the same sort of thing that you do with the polynomials. You remember what we did with the polynomials? We played this game, right? It was something like this, and we wanted to know what it looked like near one of the zeros, right? So near a zero or pole. Okay. And when I say pole, I mean a place where the denominator is zero. Okay, so we have these rational functions, right? It's a polynomial over a polynomial, right? You've got something like polynomial over a polynomial over a polynomial, right? The zeros are where the top is zero. The poles are where the bottom is zero, right? Where the vertical asymptotes occur. Yeah, Lauren.
So the x-intercept, because I got a little confused on the homework,
Yeah.
the x-intercept is where the top is equal to 0, right?
That's right, that's right.
Okay, because I did that and I wasn't getting the right answers.
It should have given you the right
Okay.
answers, right? Because, right, that will tell you where the top is zero. If the top is zero, then the whole function will be zero.
Right, okay.
Right? And so that will tell you where it crosses it should have told you where you cross the x-axis. Okay. So for a rational function, zeros occur. For a rational function, p over q, zeros occur where p is 0, and poles, at least for our rational functions, and poles occur where the denominator is 0. Right? Okay, so where the poles are basically where the function blows up. And that's actually what mathematicians say. It's not some sort of slang. If the function blows up at that point, it goes to infinity. Okay, so remember what we did for polynomials, right? For polynomials, something like x minus 3 squared, right? Do people remember how we did it? Like near 0, near x equals 0. Near x equals 0, p was basically, remember? P was basically what? 9x, right? You held the term that gave you the 0, and then you substituted in 0 for the other guy, right? You get negative 3 squared, that's 9, right? So the function was basically 9x near here, right? And near x equals 3, the other 0, right? P of x is basically what? Shreya, do you want to try?
Replace the x with the 3 to be 3x minus 9.
Exactly. 3x minus 3 squared. So, right, so, right, so right, so here's 1, 2, 3. So the thing looks like the square function, the parabola, x squared, shifted over by 3 and multiplied by 3. Okay, so it's like this, sort of a steep parabola here. Right? And you sort of guess that basically this guy looks like this.
So you substituted into the outside x but not the x inside the bracket.
You substituted into so near x equals 3, you hold the term that gave you that 3, right? So this is the term that gave you the 3, the other terms, all other terms you substitute. So this x, you substitute. X is basically 2. Okay, so the thing becomes 3x minus 3 squared. Okay, going.
Do we know where the turning point is? Not the one.
We don't.
Okay.
We don't.
And can't you not figure that out till?
Not yet. Yeah, not yet. Not until we get some calculus, actually.
Yeah.
Okay, so that's how we did for polynomials, and the same thing is going to hold for rational functions. So same approach works for rational functions. Okay, so let's take an example. Let's see. This one, so this is number 41. X plus 1 squared over x minus 1, x minus 3. Okay. Okay, so you play the game, and you say, well, where are my zeros? So where are the zeros of this function?
Your x plus 1 plus
Wherever,
equals to 0.
wherever the top is 0, right? So that's zeros at x equals -1, poles at where?
1 and 2.
1 and 3, right?
So poles are the y-intercepts, right?
No, they are where the function blows up, where the vertical asymptotes appear, right?
I thought to find the y-intercept, oh no, to find the y-intercept, you make x equals 0.
Mhm.
Yeah, okay.
Oh, so those are the same thing as vertical asymptotes.
They are where the vertical asymptotes occur.
Make mine. Oh,
Yeah, where
that
the
makes a lot of
function,
sense, yeah.
where the function goes.
So that's where it's not gonna hit.
Okay, so we know that, for example, when the line crosses at -1, we have some asymptote at 1, we have some asymptote at 3. Okay, that's what this tells us, right? And we're wondering, what happens, what does the function look like? Very precisely near these points. Okay. So we just play the same game. Say, well, okay, at x equals -1, what does it look like? Take half a minute and write down an answer. What does the function look like? Sophie, I just realized it's a contrast, the black and white. Like how children can see only black, white, and red.
You can see the black, white, and red.
At the beginning, babies can only see black, white, and red. And so I think that's what's going on.
So it should be going back to the chapter.
Yeah, I think so. Okay, who would like to say? Yeah, Caroline.
So I'm not sure if this is correct, but x equals -1, isn't it heading towards, but will never actually reach the asymptote?
We're gonna do the 0 first, not the asymptote.
Okay,
Okay, but so let me get to that question when we do the asymptote.
okay.
But so let's just talk about what happens near the 0. Well, we do the same thing as before, right? We're gonna right just plug in for the other guys and hold this guy constant. Okay. Hold. Don't plug in. Don't plug in for this guy because if we plug in, what do we get? 0. Right. Which tells us that we get close to 0, which we knew, but that's not really what we're thinking about.
Yeah, so why are we, just because in all of the homework we never plugged x back into the problem, you always just plug to find. Yeah. You never plug x back in, so what are we finding for?
What we're finding is the behavior near x equals 1. So what we're asking is this question. What does R look like near x equals minus 1? We know what it looks like at minus 1. It's 0, right? But we're wondering, what about if you're really close to x equals minus 1? Well, in that case, x is basically minus 1, and so R of x is basically 1 over negative 2, negative 4, and this x plus 1 squared. Okay, because x is basically negative 1. Okay, and so this is 1 over 8 times x plus 1 squared. Right? So the function looks like just the square function shifted over to the left by 1 and slowed down, squashed by a factor of 8. Okay. Right.
Why didn't you plug the 1 into that x?
Because if we do, then what do we get?
1 plus 1.
1 plus negative 1, which is 0.
Oh, so just,
Which wouldn't give us any. Okay, so this thing looks like a parabola, but a bit of a slow parabola. Okay. Right. So a parabola was sort of a y axis.
How do you know that it gets to the y-axis?
Because the function look at it, it's the x plus 1 squared function.
Oh, but
Right.
you just like chose a random point, you didn't actually figure out where it hit on the graph.
Oh, right, that I don't know.
Oh, okay.
Yeah, I don't know where it's going to hit, but I'm, guessing.
can you find out where it's going to hit? You just find out the
Yeah,
y.
you just substitute in x equals 0.
Yeah.
Okay, and then what about near x equals 1? What does it look like? Carolina, go ahead.
Well, does that mean that you can't do it because then the denominator would be 0?
Right, so you don't want to substitute it into that guy. That's the guy you're going to hold still, right? So you will have a 1 over x minus 1.
Oh, I'm sorry, yes, I see that, okay.
And then the other guys.
Then you substitute over.
Right. So can you just do it for me, Carolina?
Yeah, so the first one would be x plus 1 squared, so it would be 2.
2 squared,
2 squared, and then below would be 1 minus 3, so it would be negative 2 squared.
just negative 2.
Negative, sorry.
Right.
So then you have 4 halves,
So you got 4,
negative half.
so this becomes negative 2. Okay. So we get r is basically negative 2 over x minus 1. Okay, so you're going to get that? Okay, that's basically all there is to this technique. Okay, and so what do you know? You know that the thing looks like the 1 over x function, right? Looks like the 1 over x function, but it's multiplied by negative 2, so it's flipped and then it's stretched, right? It's flipped across the x-axis, right? So it's flipped over, right? And then it's scaled by 2, so everything is multiplied by 2. So it's sort of a
Isn't it moved over as well?
oh, yeah, and it's moved over, moved over by 1. So here's 1. So it's like this. So let me move it over here. Wait, I got it backwards. I've written it upside down. It should be this way, this way. Right? And so now we're starting to see what the thing looks like. because here's 1 over x. Here's 1 over x, right? And so we flip it over, right? So you get this guy. I don't have any color chalk, but I use double line. This guy, and this guy. Right? That's what it looks like. Yeah, look.
Wait, so how do you know where it is on that graph? Like, I get it's shifted over 1, so
Here's the one.
but it can't go past the 3.
Right. We only know basically. So I'm connecting lines. I'm connecting lines because that's what you'll do in the end.
Yeah.
But all this tells us is behavior near 1, behavior near -1, and we'll talk about behavior near 3 next.
Okay.
We're not going to go like this because once you get close to 3, something else happens.
Right. Okay.
Okay, we have to figure out what happens near 3. It's not, so near x equals 3, we do the same thing. We get 3 plus 1 squared, 3 minus 1, that's 2, and then 1 over x minus 3. Right, so 16 over 2, 8 over x minus 3. Right, so the guy looks like basically like the 1 over x function. So here, like this, and then here, like this. This is the information we just got. Yes.
Could you explain the one that you just drew? It looks almost like a parabola.
Yeah. So down here, you see what's going to happen. It goes towards infinity here, goes towards infinity here. It doesn't touch the line. It comes up and it must curve around. It's
Okay.
like here.
Okay.
Yeah, it must curve around without touching here. Okay. And then there's maybe one bit more. If you want, you can put this together with the information we were talking about last time, right? The horizontal, for example, the horizontal asymptotes. We've left those out. What's the horizontal asymptote of this as x goes to infinity? Can anyone just look and tell me? 1. Right. We have x plus 1 squared on the top. We have x, we just look at the top term. It's x squared. The top term is x squared. Right? On the top, the highest degree term is you're going to get x squared. Same thing here. The highest degree term, you're going to get x squared. Right? So this goes to the line y plus 1. Right? So this is 1. Like that. Yeah.
What does that tell you, though?
It tells you that the function will tend towards that line as you go towards infinity.
Oh, so it tells you what. Wait, where's that? The one. The one. Oh.
This,
Oh.
right? Remember we figured out already that this thing looks sort of like a parabola here, a slow parabola here, and it's gonna come this way towards the asymptote. Yeah.
Does an asymptote mean that it's approaching that from both, when it goes in both directions?
Not necessarily. Yeah, but in this case, yes, because the function we see Rx for x large, Rx is basically x squared over x squared. Right? Well, that's 1. Right? If you take x to be positive or you take x to be negative, that's going to give you 1. Yes, it is.
But a horizontal asymptote never exists, or is there always one?
Could be that one doesn't exist. Actually, in the homework that I'm going to give you today, you will have functions that get close to a line that's not horizontal. Okay, you have a function and it gets close to this line, say. Okay, and this is what's called a skew asymptote. Okay, It'll explain it in the problem. Say this function will have a line that it approaches, but that line is not horizontal. It's actually a line with some slope. This sort of situation is called a skew asymptote. It'll ask you to show that some function has a skew asymptote. Okay, so it's not necessarily true that the function could have a horizontal asymptote.
And then when finding a horizontal asymptote, is it always going to be the leading coefficient of the top divided by the bottom?
If there is a horizontal asymptote.
So when would it equal 0?
Well, you could have something like this, 1 over x.
And
Right? As x goes to infinity, this thing approaches the 0, the line 0. Wait, say the question you said before. Is it always true that the horizontal asymptote is?
the leading coefficient of the top divided by the leading coefficient of the bottom.
No, I'm sorry, no, that was not true. That's not true. That's true. Right, so let's say again, how to find horizontal asymptotes. You know, basically, if you have something like, I don't know, like x squared, 2x squared, x minus 1 over x cubed, then then you see what happens. The top, you know, this is 2x cubed minus 2x squared over x cubed, right? And as for x large, for x either positively large or negatively large, and basically you can ignore all lower order terms. So you get 2x cubed over x cubed. That's set 2. Okay. So in this case, yeah, if the top and bottom coefficients, if the top and bottom, if the degrees are the same, what you said is correct. Okay. If the degrees are the same, what you said is
We
correct.
have a problem with the degrees being the same.
Right. So if the degrees are the same, for example, like 2x squared, x minus 1 over x minus 4, right? Then you say, well, this thing, again, is basically, well, this is 2x cubed minus 2x squared over x to the 4th, right? And then, again, you just take the top, you take the terms of highest degree. This thing is basically, you know, you can basically ignore this guy, right? Okay. And so what you get, this thing is 2 over x, right? And so when x goes to infinity, when x goes to positive infinity, this thing drops down to 0 from the top. Right? Do you see that? Right? As x gets gigantic, 2 over x becomes very small. Right? 2 over 2 millions, 2 billions, 2 trillions, 2 quadrillions, whatever. Right? So in that, so that's all there is to it. It's not well,
Okay, I have 2 questions.
Yeah.
One for that, would the horizontal asymptote then be 0?
yeah.
Okay. And then the other question is, weren't we doing long division and we didn't have the same degree on top and bottom? Like, when is it that you have to do long division? Because I thought it was for the problems like that where you had different degrees.
You could do it, but you could also do it this way. So you could do the long division. The long division actually is most relevant when you have the degree that's bigger than. But I mean, in finding asymptotes, actually you don't need to do long division ever.
So since we're not going to have anything where it's bigger on top and smaller on bottom, we're never going to have to do long division.
No, that's not true. So the long division actually gives you some you know, it's a way of expressing the function in the cleaner. So, you know, like last time, right, we had this guy, right, 3x plus 2, x over x minus 3 turn out to be 3 plus 1 over x plus 3.
Yeah.
Okay. So,
Oh, so then you have the same degree?
yeah.
So why didn't we do long division for the first one? Sorry, I think this is a lot of questions.
No, it's okay. We could have. We could have, and that would have given us, you know, so like, okay, so you could have. So you take your 2x cubed minus 2x squared, you divide it by x cubed. Okay. What do you get? You get 2x cubed, right? So minus 2x squared, right? So this is your remainder, right? And so you get that this thing equals 2 minus 2x squared over x cubed.
And then you just do the 2. Okay, so we can do it either way.
Yeah,
basically.
yeah, yeah.
Okay.
Okay, so this turns into 2 minus 2 over x. 2 minus 2 over x. Right? And you see, you know, as x goes to infinity, this turns into 2.
Okay.
Okay. So the long division is sort of a cleaner way of getting more getting information out of it. Because this tells you exactly what the thing looks like. Right? It's not just telling you the asymptote. It tells you exactly what it looks like. Right? It looks like the function y equals 2, and then subtract off this 2 over x guy. Right? So, yeah, it was,
For the graph,
Yeah.
on the -1, does the right side, so it doesn't touch the asymptote?
it goes through
It's
it.
like that.
It goes through it like that.
So it does go through?
Yeah. It has to, right? It has to.
Then why does the other side not go
That's not clear actually. We don't really know. Maybe it goes up and then comes down. We don't actually know. We don't actually know. I'm just making some sort of guess here. It could go up and then come down on top to the top of it. Right? But in the long run, it approaches the line. That's all you know. Yeah, but I just my guess is that it probably goes from the bottom. Okay, I didn't mean to spend so much time on this. The point was basically it's the same procedure as before, right? To figure out how you behave near 0 or near a pole. You just play this game of substituting in everybody except for the term that gave you that 0 or pole. Okay, that's it. Next time I'm thinking of doing the so-called upside down class, that is giving the students the lectures recorded and then having them come in and just ask questions and do problems in class. I don't know if that will be more effective or less effective.
For the whole semester? It's a lot of pressure.
We'll see. We'll see.
I mean, it'll be better but for like seniors.
If it becomes a complete failure, then of course I'll refer.
Yeah. Because you have to do homework and watch the lecture.
Yes.
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 I guess you didn't assign homework.
Hmm?
I guess if you did that class, but you didn't assign homework.
No.
Because then it's like, instead of like 3 periods a week, it's like 6 periods a week.
Yes.
Yeah. I like this way.
Okay. Okay. So okay, upwards and onwards, as one of my dear old professors used to say. Okay, chapter 5, exponential functions. Okay. So, like I said, this course is called transcendental functions. None of the functions we've done so far are transcendental. This is the first example of something which is called a transcendental function. I'm not going to even explain what transcendental function means, but just to give you sort of an analogy, there's something called an algebraic number. Okay, and an algebraic number is something that occurs as a root of a polynomial with rational coefficients. Okay, so for example, like x squared x squared minus 2 equals 0, right? So the square root of 2 counts as an algebraic. Square root of 2 is a root of this thing, and so it's an algebraic number. Okay, 1 is an algebraic number, right? Because it's the root of x minus 1, right? Lots of numbers are algebraic numbers, but it turns out that there are some numbers that you can't reach in this way. Okay. For example, pi is not an algebraic number. You can't get pi as the root of the sort of polynomial with rational coefficients. Okay, not an algebraic number. Okay, and so it's what's called a transcendental number. And another number that we'll get to shortly, E. How many of you have heard of E before? Okay, most of you. E also is not an algebraic number, but a transcendental number. Okay, so you want to think that there are these sort of like mundane guys, the algebraic guys, and then there are these sort of unusual guys, the transcendental guys. In the same way, the functions we've been dealing with up until now are sort of the maybe not so interesting guys, and now we're starting to get into the transcendental, maybe more interesting functions. Not to say that they were not interesting, but that there's something better about these guys. Okay. Okay, so exponential growth. I'm sure you've all heard of this sort of thing, right? So to give an example, right, suppose that Professor Professor M, decides to encourage the students to come to class. He says, we'll give 2 cents, 2 to the x cents if a student attends x classes in a row. Right? So let's say that there are 30 classes, right? And student 1, of course, skips every other class and ends up attending 15 classes, right? And because none of them were consecutive, gets only 2 cents per class, right? So student 1 gets 30 cents, right? Attends every other class, right? Student 2, on the other hand, attends every class.
And how many classes are there?
30, right? And so gets 2 to the 30 cents. 2 to the 30 is something like $10 million. Okay, it's about $10 million, and so student 2 retires and. Okay, so this is the difference between linear growth, right? Every time student 1 attended class, which was every other class, she got 2 more cents. So 2 cents here, 2 more cents, 2 more cents, 2 more cents, 2 more cents. Right? This is linear growth, right? The rate of change is constant, right? Exponential growth is something much, much, much faster. Okay. Okay. Right. So this is our. Maybe our first example of an exponential function. Okay, so f of x is 2 to the x, right? 2 2 to the x. Okay, so 1, 2, 3, 4, 5. I don't even have enough space. Right? You see, I don't even have enough space to go up to 2 to the 5th here, right? So here's 1, 2, 3, 4, 5, right? At time 1, you get 2 to the 1, right? At time 2, you get 2 to the 2, that's 4, 2, 4, 8. At time 3, you get 8, at 4, you get 16, we've already reached the top of the board, right? At time 0, what do you get?
1.
2 to the 1, and 2 to the 0, that's 1. At time negative 1, you get 2 to the negative 1, that is to say 1 half, right? Right, at time negative 2, you get 2 to the negative 2, that's 1 over 2 squared, that's 1/4, right? 1/8, 1/16, 1/32, etc. So the function goes like this. Right. Okay. What's 2 to the 3 halves? Just to remind you of your previous knowledge. What's 2 to the 3 halves? What does that mean?
2.
Yes.
Square root of 2 square root, or no, cubed root of 2 squared.
Cube root. No, you gotta make the first one.
Okay, square root of 2 cubed.
Square root of 2 cubed. You can think of it that way. You can think of it as 2, the square root, right? 2 to the half, that's to say the square root of 2 cubed. You could also think of it as 2 cubed to the half, right? Using your properties of exponents, right? That's the square root of 8, right? You could also think of it using properties of exponents. You could think of it as 2 times, right? 2 to the 1 times 2 to the half, right? Because when you multiply a function, you multiply these guys with the same base, you add the exponents, right? So this is 2 times root 2, and all these answers are the same, of course, right? Root 2 cubed, root 2 cubed, 2 roots of 2, or root 8 are all the same thing. They better be. Right? Okay. So that's just your first reminder. 2 to the 3.1. What's that? Well, this is the same sort of question, actually. Right? We could write this. Let's use this thing. How should we write it using this property, the multiplication turns into summing of exponents property? Well, we've got a sum here. We'll write it as a product, right? 2 to the 3 times 2 to the what then? Right. So 8 times the 10th root of 2. Right? Okay. Or if I have 2 to the 3.14, I can write that as 2 to the 3 times 2 to the 10 times 2 to the 4 100ths. Okay, so those are review questions, but now I'm going to ask you a real question. What is 2 to the 5? Right? 2 to the 5, right? 5 is somewhere around here. Right? Our graph appears to go through it. There should be some value for 2 to the 5. What is that value? How do you think, what do you think? Actually, the answer is you don't know. You don't know yet. But what do you think it ought to be? Lauren?
Would you use a log?
No, not yet at least. Carolyn?
Well, wouldn't it just be what we were doing 2 to the 3 times 2 to the 1 over 10 times 2 to the 4 over 100, so on and so forth and so forth? So it just keep getting longer and
So you have an infinite product, right? You
Right.
have this thing, 2
That we
to
would never be able
2
to-
to the 1, and 2 to the 4, and this.
So we get a rough estimation that we would know exactly. Okay.
Yeah, and in fact, this is how one does it. Basically, and we're not going to do this, but you take it, you consider 2 to the 3, 2 to the 3.1, 2 to the 3.14, 2 to the 3.141, et cetera. And it turns out that those numbers get closer and closer to some number, and that number we call 2 to the pi. Okay, so this is what you go on calculus. This is called taking the limit, right? You take the limit of some sort of sequence of numbers, and they converge to something. Okay, so but at this point, we have no understanding, no real understanding at this point of irrational powers. So right now we don't have any understanding of rational powers, but let me just say to you, as a fact, it is possible to define them in such a way that the standard properties of exponentiation hold. Okay, and by the standard properties, I mean, a to the n, a to the n is a to the n plus n, a to the n to the n is a to the n. The standard properties of exponentiation. Okay, so for example, it makes sense to talk about square root of 2 to the square root of 2 to the square root of 2. Okay, that actually makes sense. And actually, you can tell me what this is if you know the standard properties of exponentiation. What is it? Okay, other two.
The first one is 2 to the 1/8.
Well, let's think. Something to the something to the something is going to be that something to the product, right? Something to the m to the n
Okay.
is going to be the base to the product of this two. Well, what's the product of root 2 of root 2? 2. Right, so we get root 2 squared. Well, what's root 2 squared? 2. Okay, so it looks mysterious, but it's actually somebody you know. Okay, it's in disguise. Okay, what's this? Well,
Do you subtract the powers, so it'd be 10 power pi plus 2 minus pi.
yeah, you can bring this guy to the top, say, right, 10 to the negative pi plus 2, right? And then you just, when you multiply guys with the same base, well, you add the powers, right? So you get 10 to the 4th, 10,000.
Wait, what? Can't you just subtract?
Sure.
So but wouldn't that give you negative, if
You
you
get-
subtract the bottom from the top, you get negative pi?
No. You get this 10 to the pi plus 2 minus pi minus 2, minus quantity.
Oh.
Right, so you get 0, you know, the pi's would cancel, you get 2 minus minus 2.
Okay.
What about this one? You just add them, right? So you get 3 to the 4, 81. Okay. And what about this one?
So it'll be root 3 to the power of 4 pi.
Right. Root 3 to the power 4 pi. Right.
And then
Who sees how to make this one more simple? Simpler. Carol?
Would you take the 4 to move it, so it'd be 4 through, but
It's not the 4th root, but the 4th power.
The fourth pi.
Yes, the 4th power of 3. Now you can rewrite it like this, right? Right? Because this is the same thing as that. Right? So you can take the 4th power first, right? This thing is root 3 to the 4 pi. That's the same thing as root 3 to the 4 to the pi. Right? To the 4 to the pi. Right? So root 3 to the 4th, that's 3 squared, 9. So it's 9 to the pi. The moral is simply that irrational powers can be dealt with just like with can be dealt with just like with normal powers. Have fun tonight. Maybe I'll bring